Welcome to our Quantum Deep Dive. Today, we're exploring a pretty fundamental question about our very existence, and we're using an essay by Jorg Oe Schneepatt as our guide. It's a journey that starts with, well, the biggest question of all, and ends with one of the smallest, most exotic particles we know.
I mean, really think about it. This is one of the biggest mysteries in all of science. Our best theory, the Big Bang, tells us that the birth of the universe should have created equal amounts of matter and its mirror image, antimatter. But if that happened, they would have just wiped each other out, leaving behind a universe filled with nothing but energy.
And yet here we are, you, me, the planet, all of it. So the crucial point is, something tipped the scales in favor of matter. To figure out what that was, we need to dive deep into the subatomic world and meet a very, very peculiar little particle.
Okay, let's get into it. Before we meet our star particle, we really need to understand the cosmic battlefield it was born on. I'm talking about the epic battle between matter and antimatter. It's a story that basically defines our entire reality.
Now, antimatter isn't just something from Star Trek, it's real. The physicist Paul Dirac predicted it way back in 1928, just by doing the math. He saw his equations worked for an electron, but also for a particle with the exact same mass, just a positive charge. And you know what? Just 4 years later, they found it, the positron. It proved Dirac was right and totally opened up a new way of looking at the universe.
Okay, now look at that third row down. Annihilates upon contact. This is the key. A proton and an antiproton, an electron and a positron. When these opposites meet, they don't just collide, they obliterate each other. Poof! Their mass is converted into a burst of pure energy, exactly like Einstein's famous equation, E equals mc squared says it should. It is the most efficient, most powerful energy conversion possible, period.
So if everything should have been annihilated in a flash of energy, how on earth did matter survive? To find the clues, we have to stop looking at the big guys like protons and neutrons and zoom way, way in on their fundamental building blocks, the quarks.
The whole idea of quarks came about in 1964. Physicists Murray Gell-Mann and George Zweig were trying to make sense of this whole zoo of new particles they were discovering in their accelerators. They realized if you just imagined a few fundamental building blocks, you could explain everything. They called them quarks, and they're glued together so tightly by something called the strong force that we have never, ever seen one all by itself.
And this table here, it shows the family structure perfectly. Quarks come in 3 generations, and each one is heavier than the last. Generation 1, that's the up and down quarks, makes up all the stable matter in our everyday world. But generations 2 and 3, they're much more exotic, heavier, and super unstable. And our particle of interest, the strange quark, sits right there in that second generation.
Right, so for every single quark we've just seen, there's an antimatter twin, an anti-up, an anti-down, and so on. Today, we're zeroing in on the anti-strange quark. So what is it that makes this one particular piece of antimatter so special for understanding our entire universe?
This chart lays it all out pretty clearly. As you can see down at the bottom, their mass is identical. But look at the rows above it. The electric charge flips from -1/3 to +1/3, and this really interesting quantum number, which they fittingly called strangeness, flips from -1 to +1. That little property, that strangeness, is a crucial hint that we're going to come back to.
These properties, they dictate everything about how this particle behaves. For instance, having a spin of 1/2 makes it a fermion, which just means no two can ever be in the exact same quantum state. And that anti-color property, well, it's not a real color. It's a type of charge for the strong force, and it means it's powerfully glued to other quarks. This is what traps it inside bigger particles, like kaons, which are absolutely vital to our story. Okay, but if these particles are so incredibly rare and they disappear in a flash, how do we even know they exist? I mean, you can't just find them lying around. We actually have to create them. And to do that, we need some of the most powerful and complex machines ever built by humankind: particle accelerators. As you can see on this timeline, the journey from just an idea to actual proof took over 40 years. It started with Dirac's pure math in 1928, got a real theoretical framework with the quark model in '64, and then finally, scientists found experimental evidence in the late '60s and early '70s at labs like SLAC and CERN, where they saw the signatures of these particles in their high-energy collisions.
You know, it's this incredibly delicate dance of creation and detection. You can't see an anti-strange quark directly because it can't exist on its own. The instant it's created from all that collision energy, the strong force just grabs it and binds it with another quark. So what we do instead is we look for the particles it helps create, like the K+ meson, which the source material tells us is made of one up quark and one anti-strange quark. So by studying the K+, we're really studying the anti-strange quark hidden inside.
And this is where it all comes together. Studying these particles isn't just some academic exercise in a lab. It's like a form of cosmic archaeology. By making these particles, we are literally recreating the conditions of the first tiny moments of the universe, to look for clues about where we came from.
This is the crucial point. As Jörg Ove Schneppert writes, these particles are basically fossils. They're sensitive signatures from the first microsecond after the Big Bang. Their very existence, how they behave in our experiments, that can tell us exactly what the universe was like at the dawn of time.
Right. In this extremely hot, unbelievably dense state, a state we recreate in miniature at places like the LHC, protons and neutrons couldn't even exist. It was so energetic that quarks and the gluons that bind them just roamed free in this primordial soup. The number of strange and anti-strange quarks that pop into existence in this plasma gives us a direct measurement of the temperature and conditions back then. They're like a cosmic thermometer.
Okay. A cosmic thermometer is pretty cool, I'll admit. But how does a particle in some primordial soup explain why our entire universe is made of matter and not just nothing? Where's the connection to that great big imbalance we started with?
The connection is through this subtle but really profound effect called CP violation. Now, I know that sounds super technical, but all it really means is that the universe treats matter and antimatter just a little bit differently. There's a slight preference. And one of the very first places this was ever seen was in the decay of those kaons we mentioned, the particles made with strange and anti-strange quarks. Now, the effect they saw isn't quite big enough to explain the whole cosmic imbalance, but it was the smoking gun. It proved the laws of physics aren't perfectly symmetrical. It proved there's a loophole that allowed matter to survive.
So, the anti-strange quark is a clue to our past, a key to understanding why we're even here to ask the question. But could it, and antimatter in general, also be a key to our future?
While the potential is enormous, but let's be real, so are the challenges. As this chart kind of shows, some applications are a lot closer than others. In medicine, for example, things like PET scans that use positrons are already a reality. But for those truly visionary ideas, like energy and propulsion for starships, the main roadblock is storage. Remember, antimatter annihilates on contact with normal matter, so just trapping it is incredibly difficult.
But the payoff, the thing that really captures everyone's imagination, is energy. Matter-antimatter annihilation is, hands down, the most efficient energy source known to physics. It converts nearly 100% of the mass of the particles into pure energy. To put that in perspective, nuclear fission is less than 1% efficient. The potential here is almost unimaginable.
And that kind of brings us full circle, doesn't it? From a tiny, fleeting particle that helps explain our distant past to a potential technology that could define humanity's far future. The anti-strange quark is just this perfect example of how, in physics, even the smallest, strangest things can hold the answers to the very biggest questions.
We really hope you enjoyed this quantum deep dive. This explainer was based on the fantastic essay Anti-Strange Quarks by Jörg Ove Schneppert. For more on this and other deep topics in physics, you can go check out Schneppert.de. Thanks for watching, and goodbye.
Schneppert.de is a private project by Jörg Ove Schneppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.